programming languages typically support a set of operators, constructs which behave generally like functions, but which differ syntactically or semantically from usual functions. Common simple examples include arithmetic and logical operations. More involved examples include assignment, field access in a record or object, and the scope resolution operator. Languages usually define a set of built-in operators, and in some cases allow user-defined operators. Syntax. Syntactically operators usually contrast to functions. In most languages, functions may be seen as a special form of prefix operator with fixed precedence level and associativity, often with compulsory parentheses e.g. function list. Most languages support programmer-defined functions, but cannot really claim to support programmer-defined operators, unless they have more than prefix notation and more than a single precedence level. Semantically, operators can be seen as special form of function with different calling notation and a limited number of parameters. The position of the operator with respect to its operands may be prefix, infix, or postfix, and the syntax of an expression involving an operator depends on its arity, precedence, and associativity. Most programming languages support binary operators and a few unary operators, with a few supporting more operands, such as the operator in C, which is ternary. There are prefix unary operators, such as unary -x, and postfix unary operators, such as post-increment x++, and binary operations are infix, such as x plus y or x equals y. Infix operations of hierarchy require additional symbols, such as the ternary operator in C, written as B, C. Indeed, this is the only common example. It is often referred to as the ternary operator. Prefix and postfix operations can support any desired arity, however, such as 1, 2, 3, 4 plus. Occasionally, parts of a language may be described as match-fix or circumfix operators, either to simplify the language's description or implementation. A circumfix operator consists of two or more parts which enclose its operands. Circumfix operators have the highest precedence, with their contents being evaluated and the resulting value used in the surrounding expression. The most familiar circumfix operator are the parentheses mentioned above, used to indicate which parts of an expression are to be evaluated before others. Another example from physics is the inner product notation of Dirac's bracket notation. Circumfix operators are especially useful to denote operations that involve many varying numbers of operands. The specification of a language will specify the syntax, the operators it supports, while languages such as Prolog that support programmer-defined operators require that the syntax be defined by the programmer. Semantics. The semantics of operators particularly depends on value evaluation strategy and argument passing mode. Simply, an expression involving an operator is evaluated in some way, and the resulting value may be just a value, or may be an object allowing assignment. In simple cases, this is identical to usual function calls. For example, addition x plus y is generally equivalent to a function call add unless than comparison x and lt, y to lt, meaning that the arguments are evaluated in the usual way, then some function is evaluated and the result is returned as a value. However, the semantics can be significantly different. For example, in assignment A equals B, the target A is not evaluated, but instead its location is used to store the value of B, corresponding to call by reference semantics. Further, an assignment may be a statement, or may may be an expression with the value itself either an R value or an L value. As another example, the scope resolution operator and the element access operator operate not on values but on names, essentially call by name semantics, and the value is a name. Use of L values as values of operator expressions is particularly notable in array indexing and unary increment and decrement operators. In C, for instance, the following statements are legal and well defined, and depend on the fact that these operators return an L value. An important use is when a left associative binary operator modifies its left argument and then evaluates the argument as an L value. This allows a sequence of operators all affecting the original argument, allowing a fluent interface, similar to method cascading. A common example is the NLT and LT operator in the C++ IOStream library, which allows fluent output as follows: user-defined operators. A language may contain a fixed number of built-in operators, or it may allow the creation of programmer-defined operators. Some programming languages restrict operator symbols to special characters like plus or equals, while others allow also names like div. Most languages have a built-in set of operators but do not allow user-defined operators, as this significantly complicates parsing. Many languages only allow operators to be used for built-in types, but others allow existing operators to be used for user-defined types. This is known as operator overloading. Some languages allow new operators to be defined, however, either at compile time or at runtime. This may involve metaprogramming, or within the language itself. Definition of new operators, particularly runtime definition, often makes correct static analysis of programs impossible. Since the syntax of the language may be Turing complete, so even constructing the syntax tree may require solving the halting problem, which is impossible. This occurs for Perl, for example, and some dialects of Lisp. Examples. Common examples that differ syntactically are mathematical arithmetic operations e.g. and gt are for greater than, with names often outside the language's set of identifiers for functions, and called with a syntax different from the language's syntax for calling functions. As a function, greater than would generally be named by an identifier, such as gt or greater underscore than, and called as a function as gt. Instead, the operation uses the special character in gt, and infix notation as x and gt, y. Common examples that differ semantically are Boolean operations, which frequently feature short-circuit evaluation, e.g., a short-circuiting conjunction that only evaluates late arguments if earlier ones are not false, in a language with strict call-by-value functions. This behaves instead similarly to if-then-else. Less common operators include comma operator, ef, dereference operator, *p, an addressive operator, and amp-x, or ternary operator, number equals spell underscore out underscore numbers. 42 Elvis operator, x, y, null coalescing operator, x, question mark, y, spaceship operator, x and lt equals and gt, y. Compilation. A compiler can implement operators and functions with subroutine calls with inline code. Some built-in operators supported by a language have a direct mapping to a small number of instructions commonly found on central processing units, though others may have complicated implementations. Operator overloading. In some programming languages an operator may be ad hoc polymorphic, that is, have definitions for more than one kind of data. Such an operator is said to be overloaded. In languages that support operator overloading by the programmer but have a limited set of operators, operator overloading is often used to define customized uses for operators. In the example, if order_date and GT, December 31, 2011, and order_date and LT, the 1st of January 2013, then continue, else stop. The operators are and GT and LT. Operand coercion. Some languages also allow for the operands of an operator to be implicitly converted or coerced to suitable data types for the operation to occur. For example, in Perl, coercion rules lead into 12 plus 3.14, producing the result of 15.14. The text 3.14 is converted to the number 3.14 before addition can take place. Further, 12 is an integer and 3.14 is either a floating or fixed point number, so the integer is then converted to a floating point or fixed point number, respectively. JavaScript follows opposite rules. Finding the same expression above, it will convert the integer 12 into a string 12, then concatenate the two operands to form 123.14. In the presence of coercions in a language, the programmer must be aware of the specific rules regarding operand types and the operation result type to avoid subtle programming mistakes. Operator features in programming languages. The following table shows the operator features in several programming languages.